would be the contour integral. And so you can use complex analysis to do the contour integral. I'll just, as with Laplace transforms, we usually use lookup tables, but I'll just quickly mention you can numerically do this, or you can use complex math to do the inverse Z transform. The limitation is the contour of integration must be within the region of convergence. Of course, the more common method is look it up in the Z transform table. Don't forget the region of convergence using two-sided transforms. In a moment, we'll do partial fraction expansion example using the lookup table method. Another method can be used for Z transform inverse transform is a power series expansion or long division. It's just best seen by example. And so here I have an x of z. It's z over z minus 0.1, or could it be written as 1 minus z minus 1 over 10. Here the ROC is magnitude z greater than the pole location 0.1. So this tells me this is a right-sided sequence or causal sequence. So to find the inverse transform, I just divide the denominator into the numerator. And so this goes into z just one time. So that's my first value. And so 1 times z minus 0.1 is subtracted from z, and I have a remainder of 0.1. I have to multiply by 0.1 z to the minus 1. I multiply that by z minus 0.1, and I get 0.1 minus 0.01 z minus 1. That's subtracted from 0.1. And I get 0.01 z to the minus 1 remainder, and I keep repeating. And this goes on infinitely, but I can see the next value is 0.01 z to the minus 2 will have to be the next multiplier. And so at the numerator, I can read directly off the values of x of n, because the definition of the Z transform is that x of n multiplies z to the minus n. Well, x of 0 multiplies z to the minus 0, x of 1 multiplies z to the minus 1, x of 2 multiplies the z to the minus 2. And so just reading from the top, x of 0 is 1, x of 1 is 0.1, and x of 2 is 0.01. And so we can read the values of x of n straight from the values resulting from our long division. If the sequence is left-sided, then the ROC will go the other way. And so you just change the order of your long division. And when I divide this now into z, my first value is to multiply by minus 10z. And so minus 10z gives me z minus 10z squared when I multiply that times the minus 0.1 plus z. When I subtract that from z, I have a remainder of 10z squared. And of course, I now have to multiply minus 100z squared. When I multiply minus 100z squared, I get 10z squared minus 100z cubed. I subtract that off, I get a remainder, and so forth. And so the values of x now, from the definition of the Z transform, so x of minus 1 multiplies z, x of minus 2 multiplies z squared, and so x of minus 1 must be minus 10, and x of minus 2 must be 100, and so forth. I continue infinitely for that Z transform. I'll just point out another example where the division ends. And so this is the example we did where the sequence was 1, 1, 1. We found that Z transform. but we're going to do long division. And so I'm going to multiply top and bottom by z to the 4. And so the denominator is z to the 4 minus z cubed when I do that multiplication. And I divide that into the numerator. So first value is 1, so I get z to the 4 minus z cubed, subtract that, and I have a remainder z cubed minus 1. Now I multiply by z to the minus 1, get z cubed minus z squared. When I multiply that, subtract, I get a remainder again. And I repeat this until this last step, I have a remainder z minus 1. I multiply z minus 3 times z to the 4 minus z cubed. I get z minus 1, and the remainder is 0, and it terminates. And notice that my sequence is the coefficients here, because the z transform, of course, is x of n, z to the minus n. And so the value that multiplies z to the 0 is x of 0, so that must be a 1. X of z to the minus 1 multiplies x of 1, so of course that must be a 1 too. And so I have 4 1s. So my sequence is 4 1s, and it terminates. In general, you may have forms of x of z where the fractions of x of z aren't in your z transform table. Just as in Laplace transform, you use a partial fraction expansion to simplify complicated x of z. We'll just assume that we have first order poles. Higher order poles, repeated poles, are just a little more complicated, but the first order poles will illustrate the process. Our transfer function will be numerator over denominator, where the degree of the numerator must be less than the degree of the denominator. If it isn't, you must first do long division. And until the numerator is a lower degree than the denominator. To do the partial fraction expansion, first set the numerator is a factor of z times something, and we'll call that something q of z. So rewrite the numerator as z times q of z, and so we'll have z q of z over some number of first order poles in the denominator. We want this to equal a partial fraction expansion where we have z times c sub a for the numerator and z minus p sub a for the denominator. And so this is the form of first order poles in z transforms. And so canceling z on both sides of the equation, we'll have q of z over the denominator again must equal the sum of the first order poles, and we need to determine the coefficients for the numerators. And so if we multiply out some particular pole on the left side, on the right side, this pole multiplies the sum of all the individual terms of the partial fraction expansion. If we evaluate this at the location of the pole, we note that this becomes 0. However, there's one term here that's going to have the same pole location, so we have 0 over 0, and that will be the only term that will appear. So c sub k associated with p sub k, this pole that we multiplied both sides by. And so z minus the pole times q over d of z evaluated at p sub k must equal c sub k, since all the other terms on the right-hand side are multiplied by 0. So once you solve for those c sub k's using that technique, then we can go back to the original definition for x of z and bring in the factor of z that we canceled on both sides originally. And so each of these are going to have the form of a first order pole. When we take the inverse transform, each one of those z over z minus a terms then is going to lead to the a to the n u of n. Of course, a is the location of each of these poles, so that becomes the pole location to the nth power times the corresponding coefficient and times u of n for each of these sequences. So this is best illustrated by an example. So if we have x of z with a pole at a half and a quarter, we need to convert that to the term where we have a z out, leading z out front. So we bring the z out front and we bring a z in the denominator to put it in that form. And so, by the way, the ROC is the magnitude of z greater than 1/2 because I have a pole at a quarter and a half, and the region would be outside the furthest out pole because a region of convergence is finite, so it cannot contain a pole. So the outermost pole sets the region of convergence. Following our formulation for this, to solve for the z equals 1/2 pole, I multiply z minus half times q over d of z. For the z equals minus 1/4, same thing. And for the pole at z equals z, which we had to introduce to put it in that standard form, cancel out the leading z, I multiply similarly by z. All of these I evaluate at the pole locations, in this case 1/2, in this case a quarter, in this case it's 0. When I multiply through by z to the minus 1/2, all I'm left with in x of z is just the 1 over z minus 1/4, and I evaluate that at z equals 1/2. When I multiply by z minus 1/4, the only one remaining is z minus 1/2, in addition to the extra z that we added to put it in a proper form. Finally, when I multiply by z, in the last case, I'm left with the original x of z, evaluated at z equals 0. That's associated with the extra pole that we added to put it in a proper format. And so substituting z equals 1/2 here, we get 1/2 minus 1/4 is a quarter over, 1 over 1/2 minus 1/4, which is at z equals 1/2. So that gives you a value of 8 for the z equals 1/2 term. Since I have 1/2 minus 1/4 is a quarter, times 1/2 is 1/8, 1 over 1/8 gives me 8. For the second term, z equals 1/4. I have 1/4 minus 1/2 gives me minus 1/4, times 1/4 gives me a 1/16, minus a 1/16, and so I get minus 16, since I have 1 over that in the denominator here. For the last term at z equals 0, I have minus 1/4 times minus 1/2 in the denominator. I get minus 1/8, so I get a factor of 8 again for this last term. All of these are multiplied through by the leading z, and so I have 8z in the numerator, 16z in the numerator. And for the last one, I have z over z, and so I just have 8 as the last term. So this gives me the partial fraction expansion for this x of z. I did need to do long division first because the degree of the numerator was less than degree of the denominator. So this is the final result after partial fraction expansion. Z over z minus 1/2 corresponds to 1/2 to the n u of n, and that's all multiplied by 8. z over z minus a quarter corresponds to a quarter to the n u of n, and that's all multiplied by minus 16. And then finally, the inverse z transform x of z equals 8 corresponds to 8 times a delta function. So we find x of n using inverse z transform and partial fraction expansions using with the lookup tables to expand the final terms. Partial fraction expansion can also be done in powers of z to the minus 1. And so if we multiply top and bottom by z to the minus 1, we can do the partial fraction expansion as we did it before, except using powers of z to the minus 1. However, in this case, we notice we have the degree of the numerator is second degree, and the degree of the denominator is also second degree. So we have to do a long division first. And so if I expand the denominator, I have to divide that into the numerator. I take out a factor of 8. And so then x of z becomes 8 plus the remainder divided by the original denominator. So that's how you would do a long division if the numerator was not less degree than the denominator. And then I can do the partial fraction expansion as before, except in powers of z to the minus 1. And I would come up with the same result as the first case. So one of the utilities of working with Z transform is that there are methods that allow you to translate a filter in continuous time to a filter in discrete time. And so you get the digital equivalent implementation of an analog filter. One of the easiest or most straightforward ways is called bilinear transform. And in short, it squeezes the continuous time frequency filter response, which goes from minus infinity to infinity, into the range of minus pi to pi, because those are the highest digital frequencies. And so the method to do that, and you convert the continuous time filter, it's Laplace transform, hc of s, into the digital filter h of z by taking hc of s and replacing the Laplace variable s by 2 over t0 z minus 1 over z plus 1. Or you can replace it equivalently, dividing top and bottom by z, 2 over t0, 1 minus z to the minus 1 over 1 plus z to the minus 1. T0 is the sample rate of the system. And so the simple substitution allows you to convert this frequency response of the continuous time system, it's a Laplace response, into an equivalent digital filter with the corresponding frequency response. So it's a very straightforward method of implementing digital filters from analog filters, or converting an analog filter to a digital filter. It has a lot of important properties. We won't go over the details, but it doesn't have the issue of aliasing the frequency response. Like a stable analog filter guarantees that the digital design will also be stable. But the price that's paid is that the frequency response is warped. It's not exactly the same as the continuous time, but it does have these other useful properties. So a simple example, if I had a Butterworth filter whose h of s was shown below, I just replace all the s's by 2 over t0 z minus 1 over z plus 1. And this would be h of z that I could use to draw my block diagram and implement my digital filter. And so if I had a z transform table, a to the n u of n would have